added a topic. L'Hopital's rule and improper integrals. Okay. So we were taking the same region, and we were rotating it around the specified axis. And we still only have one method at our disposal, really, which is perpendicular slices to the axis of rotation. But if our region that we're identifying is not entirely flush up against the axis itself, it'll generate a void, which means that we have two radii. So it'll be a washer, perpendicular, not a perpendicular. All right, so if we're rotating around the y-axis, we're on part D. That's going this way. That's a vertical axis, so right now we must slice it how? Horizontally. So again, it's not required that you see what the three-dimensional object looks like, but if you want to visualize it, it's going to be something like that and like this. So it'll be kind of a bowl, and from the outside it'll be nice and rounded, but on the inside it'll have this nice, like conical interior, nice and smooth and flat. But again, that's not really necessary. I guess the y-axis is. So what we need to do then is realize that we will have a void if we slice horizontally, yes? It's going to end up looking like this if you extend that down. Any one of these representative slices, if you do it like that, is going to look like that. Then you're going to have an interior slice, something like that, dy. So we need to have two radii. So from the axis now to the first curve is little r, and from the axis to the second curve is big R. And so notice it is going to be right minus left, which means we need to solve our equations for x. Yeah. So the first one I'll solve is y equals x squared. That's going to be x equals the square root of y, plus or minus, which one? Plus. Why is it positive square root of y? Because our x values in this case are in quadrant 1. Yeah, but if we had been in quadrant 2, the x's would be negative. And then, of course, when y equals x, x equals y. That was easy. So now we need our intervals of integration, which if you recall from last time, it was nice. It was 0, 0, 1, 1. So both the x and the y were 0 to 1. But that's not always the case. So here we go. We're ready. The volume, VOL, is equal to, what goes out front? Pi, sum of the infinitely thin slices from low to high, which is from y equals 0 to y equals 1, of beefy brackets, big R squared minus little r squared, close beefy brackets, d what? dy. Good. Anytime it's horizontal, it's dy. So now, big R is right minus left, and we have it drawn. So the curve on the right is the square root of y, and the curve on the left is actually the axis itself, which is x equals 0. So that's going to be the square root of y minus 0. One of those is the axis. And then little r is right minus left, which is x equals y on the right minus the axis x equals 0 on the left. And there's the setup. Simplify, evaluate with or without a calculator. All right, so that one was pretty nice. First time we've done the washer method with a horizontal slice. Part E, the line x equals negative 1. What type of line is x equals negative 1? It's a vertical line. So it's another vertical line. So we're going to still have to slice it horizontally. So now if you rotate this around that line, not only are you going to have a void in your slice, but you're going to have an opening in your three-dimensional object because it's going to look more like a, what's that? Yeah, negative 1. What did I say? Yeah, I'm sorry, if I said 1, I meant negative 1. I drew negative 1.
Yeah, look, I saw the vertical lines you do at the line.
Oh, yeah. Yeah, we'll highlight the axis here. There it is. There's the axis of rotation. All right, so once again, we only have one method at this point. So if it's a vertical line, we have to slice it horizontally. And we definitely have a void. So from the axis to the first curve is little r. From the axis to the second curve on the outside is big R. And so the volume is going to be pi. Sum of the infinite slices from y equals 0 to 1. Beefy bracket, big R squared minus little r squared dy. So just like in the previous problem, the curve on the right now for big R is square root of y. Minus the axis on the left would be minus negative 1. So what's that going to be? Plus 1. Good. Right minus left. Square root of y minus negative 1, which is plus 1. And little r is going to be x equals y on the right minus the axis negative 1 on the left is again plus 1. So really that's the only difference between D and E is that our radius is 1 unit longer because we're to the left 1 unit as opposed to the right. And look at this one. Part F. Line x equals 17. Where's that dude found? Yeah, way out here in France. Wow. 17. Almost off the iPad. Is that what you said? Yeah, it is. Well, it is off the graph. It doesn't intersect it anywhere. You're never going to have to rotate it, by the way, around any line that cuts right through the interior of your area. It'll either be to the left or right there at the point of intersection. But again, we have a vertical line. We only have one method at this point, which requires us to slice it horizontally. So this one, if you rotated it around, this is going to be kind of a cool looking shape because now it's the opposite of what the other shape is. It's going to have a giant hole in the middle all the way through, but from the outside now, it'll look kind of like a cone that's been truncated, and the inside has this rounded piece, so almost maybe like a Christmas tree stand. I don't know. Not that that's important. From the axis way over there to the first curve is little r, and from the axis to the outside curve is big R. So notice the two curves now change because we're on the other side. But it's really still the same idea. The volume is pi out front, the sum of the infinitely thin slices from y equals 0 to 1 of beefy bracket, big R squared minus little r squared dy. And what is big R? What is it? Big R, right minus left. Notice the axis is on the right now, so it's x equals 17 minus x equals y. 17 minus y. Not y minus 17, 17 minus y. And then little r is right minus left. That's axis on the right minus square root of y. Now, you might argue that it doesn't matter which one's on the right or left because you are, in fact, doing what to both of those quantities? Squaring it. So 17 minus y and y minus 17, when you evaluate it, it's going to give you the same answer. But do you think it matters in terms of your setup? It does. You still get points off for a reversal error, even though the answer in this case would come out to be the same. So again, you're communicating understanding of what you're doing. You're always striving to make things positive. Right minus left or top minus bottom. Just so happens with the disc washer method, one of those two curves, in each case, is the axis. You don't have a radius if you don't have an axis. Okay, so there you go. We had a couple of horizontal axes, one that was the x-axis, and then one above and one below. Then we had some horizontal or some vertical axes, one that was the y-axis, and one to the left and one to the right. Very general idea. Any questions then on the disc or washer method? Is there another method? Probably so. Yeah, there actually is. Okay. So if you look at example 8, it says the region enclosed by the x-axis in the parabola 3x minus x squared, which if you want to know what 3x minus x squared looks like, if you set it equal to 0, you could factor out an x, and you get 3 minus x. So that is a parabola that opens down, that has x-intercepts at 0 and 3. So they kind of graphed it for us. I'll just trace over it here in blue. Here's 0, here's 3, and the parabola opens down like this. So there's the graph. The region, though, is bounded by the x-axis in that parabola. So the region itself is this right here. It's telling us to take that region and revolve it around the vertical line, x equals -1. So that's the axis of rotation or revolution. And when you do that, of course, since it's not butted up against the axis, you're going to have a void, but it's also not even touching there, so you're going to have a hole all the way through it. And when you rotate that around, it looks a lot like a bundt cake or a wax ring for a toilet seal, whichever you find more appetizing today. If you've ever seen a wax ring for a toilet, they look almost like that, but that's also what a bundt cake looks like. One's just easier to eat. All right, so we want to find the volume of the bundt cake, and we certainly don't want to do it by fluid displacement, because whether it's cheese or butter, that just ruins the bundt cake. Now with the toilet wax ring, you could find it by displacement, because the whole idea behind the toilet wax ring seal is that it repels water, which is why if you've ever reset a toilet, you get that wax stuff on your hands, it's like, okay, I'm like this for the rest of my life. I have waxy fingers now. All right, it's hard to get off. It's an emulsifier. So let's just stick with the bundt cake from here on out. Right now, if we were to try and find the volume of the aforementioned bundt cake, if the axis is vertical, we would have to slice it how? Horizontally, okay? So if I take a slice all the way through this bundt cake like that, it's going to be, again, it would look like a washer, right? We'd have something that looks like this. And the radius would look like the following. I'd have to draw from the axis to the first curve would be little r, and from the axis to the second curve would be big R. But, of course, that's going to require us to do what with our equation? If we slice it horizontally, we have to solve y equals 3x minus x squared for guess what? Bless you. Anytime you slice horizontally, you have to solve your equations for x in terms of y. And how easy is it going to be to solve 3x minus x squared for x in terms of y? Not so fun. And it would require actually two separate equations. We'd have to get the right side of the parabola and the left side. It would have two equations, and it would not be fun. We would actually have to find it using a quadratic formula. Yucky, yucky, gross, gross. So is there another way? I sure hope so. Okay? I sure hope so. We would prefer, by the way, if we were just finding the area of that blue region, we would prefer to slice that how? Everything being equal, we would prefer to slice that vertically. Okay? Because from left to right, the top curve is the parabola, and the bottom curve is the x-axis, and it's beautiful, right? Besides, then the thickness would be dx. Our equation is already solved for y in terms of x. So the question is, if I slice it vertically, and now my axis rotation is also vertical, I can't use the disc or washer method. But I wonder what would happen if I took a little bitty slice of that area and rotated that thing around the axis of rotation. Well, if you want to mirror it over here, it would look like that, and it would look like this. What would the thickness of that be? dx. And remember, dx compared to delta x is a finite measurable thickness. dx is a what? Infinitely small, immeasurable distance. So that would generate kind of like a cylinder, right? We could take the volume of the outside cylinder minus the volume of the inside cylinder. But if you think about that, what is the distance between little r and big R if the distance between them is dx? It's infinitely small, right? Infinitely small. So we have a infinitely thin, essentially, with one radius, because they're so close together, it's effectively one radius. We call that a cylindrical shell. Okay? And there it is kind of shown at a different point, a cylindrical shell. So if we can find the volume of that cylindrical shell, we could then figure out what the volume of all of them are, because there are two ways to slice a bundt cake. Okay? If you've ever served a bundt cake, you probably take a slice like that, and a slice over here on the back, and you have this nice piece on your plate. Okay, you slice it all the way around, kind of like you would a pizza. But there's another way to slice a bun cake. And next time you have a bun cake party, I would encourage you to do it this way. You can get a long bread knife, come in from the top, and just slice it like this all the way around. How thick of a slice do you want? Okay, about an inch. Okay, come in an inch and slice it again. And then you scoop out the ring and you set it on their plate. All right? Who wants another slice? I want a big slice. Okay, I'm going to slice your ring right here at the very top. You're going to have the biggest piece, right? And then someone else, I want the end piece, right? You're going to have a really long, wide little ring. And you could cut out all of these little rings, right, going around in perfect concentric circles and somehow lift up the ring and set them down. Now, that would be win-win if you can get all those rings out, because guess what? It's like now a receptacle, a bowl for ice cream. It'll contain it. Genius! We should party after the AP exam. Yeah. Anyway, if I could find the volume of each of these rings, these cylindrical shells, from left to right, same thing. Add all the volumes together of the individual pieces, you get the whole thing. The question is, what's the formula for each of those? Well, would you like me to try and derive it in the time we have left before lunch? Good, I will. All right, here's your axis of rotation. X equals whatever, A. I'm going to draw it a little bit wider than it actually is. Okay? So I'm going to call this right here, in the middle, I'm going to call it R. That's my radius R. And I'm going to call the distance then from the inside to the outside, I'm going to call that W. Now this right here, I'm going to call H of X. It's just the height of the shell. All right, so instead of saying I have an inside radius and an outside radius, I'm going to let R equal the average radius, essentially. And then to the inside, yes? They are. I'm going to make my average radius be right in the middle. Okay, right in the middle. So that the smaller radius is R minus W, and my outer radius is R plus W. Are you okay with that? Now remember, how thick are each of these little cylindrical shells? Infinitely thin, which is why I want to be able to express the radius as a single letter R. Okay? So let's go ahead then and find the volume. The volume of the shell, as we're going to call it, is once again the volume of the W whole thing minus the volume of the H whole thing, just like with the washer, right? So the whole thing is going to be this right here. It's just the volume of a cylinder, right? What's the volume of a cylinder? Pi R squared H. Well, what's our radius for the big one? R plus W. And then minus the volume of the void, which, if you want to do that in a different flavor, let's do orange. We'll just get rid of this cylindrical piece here in the middle. It's like counterboring a hole. Okay, you're going to drill out the center. That's going to be pi R squared H. But now the radius of the small one is R minus W. Okay, now notice, as before, we can factor out the pi and the H. And that leaves us R plus W squared minus R minus W squared. And I will pick up here on the recording after lunch. Okay? All right, have a great lunch, everybody.